Welcome to the exciting universe of music theory. Are you ready to learn? Then let's begin. Today we will talk about scale 585, diminished seventh, which sounds like this. This scale has 4 tones, which means it is called a tetratonic scale. This is a bracelet notation diagram of scale 585. The shaded circles represent tones that appear in the scale, and they are read clockwise, starting at the top. The pitch class set for this scale is 0, 3, 6, 9. The Fort class is 428. This set is prime. The structure of a scale is a description of the interval distance between each successive tone. This scale has a structure of 3-3-3-3. The binary representation of this scale is determined by mapping tones of the scale to binary digits. Each binary digit represents a power of 2. To get the scale number, we add the powers of 2 together. The powers of 2 that are present in the scale, all added together, equals 585. That is why the scale number, in decimal, is 585. The scale number not only enumerates the scale with a unique index, but it also literally describes the tonal content of the scale. Represented as a binary number in base 2, the scale number is 001001001001. Here are the common triads present in this scale. The diagram in the center is a graph of parsimonious voice leading between triads. There are no major triads. There are no minor triads. There are no augmented triads. There are 4 diminished triads. Here is a Hamiltonian path of parsimonious voice leading that uses all the triads. Scale 585 has no modes, because every rotation of itself is the same. Imperfections are tones that have no tone, a perfect fifth interval above them. This scale has 4 imperfections. They are at positions here, 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 and here. Hemitones are instances where 2 tones in the scale are a semitone apart. This scale has no hemitones. Cohematones are instances where 2 hemitones are beside each other. This scale has no cohematones. The distribution spectra describes the size of each of the scale steps, which in turn describes how evenly spaced the tones are. A generic interval is how many scale steps are between one tone and another. A specific interval is how many semitones apart they are. The generic interval of one scale step has just one specific interval size. 3 semitones. The spectrum width of this generic interval is 0. The generic interval of 2 scale steps has just one specific interval size. 6 semitones. The spectrum width of this generic interval is 0. The generic interval of 3 scale steps has just one specific interval size. 9 semitones. The spectrum width of this generic interval is 0. The spectrum variation is the sum of all the widths, divided by the number of tones. The spectrum variation of this scale is 0. The variation of the scale is exactly 0, which indicates that the scale is perfectly even. The highest spectrum width is 0. Since is less than or equal to 1, that means this scale is maximally even. If every spectrum has exactly 2 specific intervals, we call that the Myhill property. This scale does not have the Myhill property. Since each specific interval appears in only one spectrum, this scale is strictly proper. The interval vector of a scale is a description of what intervals exist between its tones. There are no intervals with the size of 1 semitone. There are no intervals with the size of 2 semitones. There are 4 intervals with the size of 3 semitones. They are here, 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 and here. There are no intervals with the size of 4 semitones. There are no intervals with the size of 5 semitones. There are 2 intervals with the size of 6 semitones. They are here and here. Each interval does not appear in this scale a unique number of times, so this is not a deep scale. Heteromorphisms are comparisons between every interval in a set. They can be classified as contradictions, ambiguities, and differences. A contradiction exists when a small generic interval has a bigger specific size than a larger generic interval. For example, if a generic third interval has a larger size in semitones than a generic fourth interval, that is a contradiction. The number of contradictions in this scale is 0. An ambiguity exists when two intervals have the same specific size, but they have different generic intervals. For example, if a generic fourth and a generic third interval are the same size in semitones, that is an ambiguity. The number of ambiguities in this scale is 0. A difference exists when two intervals have the same generic size, but different specific sizes. For example, a major third and a minor third both have the same generic size, but they have different sizes when measured in semitones. The number of differences in this scale is 0. The coherence quotient measures the proportion of ambiguities and contradictions among a set's intervals. A scale with a higher coherence quotient is a good candidate for musical usefulness. The coherence quotient is 1. The sameness quotient measures the proportion of heteromorphic differences among a set's intervals. A scale with a higher sameness has fewer differences, so it is also a good candidate for musical usefulness. The sameness quotient is 1. This scale has reflective symmetry across 4 axes positioned at 0 semitones, 1.5 semitones, 3 semitones and 4.5 semitones above the root. This scale has the same pattern of intervals both ascending and descending, so we call it palindramic. This scale has 4 ridge tones. They are at positions here, 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 and here. The balance of a scale depends whether the tones are spaced equally enough for the center of gravity to be in the center of the scale. This scale is balanced. The inverse of a scale is a mirror image. It is what you get when the sequence of intervals is reversed. This scale is symmetrical, its inverse is the same as itself. Like all symmetrical scales, this scale is achiral, since it can transform into its own reflection by a rotational transformation. This scale has rotational symmetry at 3 semitones. For even more detail about this scale, visit ianring.com/musictheory/scales/585. If you found this video informative, please consider supporting this channel by becoming a patron. Of course, not everyone has the means to support a project like this one financially, and that's okay. But if you are able to spare just $1 a month, your help is deeply appreciated. It will not only allow others to continue enjoying this series for free, but will also go toward improving the quality and quantity of music theory resources we can provide. Go to patreon.com/musictheory and join others like yourselves who totally geek out on all this nerdy stuff. Thank you to these Patreon patrons.